In my recent video on the Heathkit IM-5225 FET multimeter, I showed a circuit similar to this with an input coming from the meter's front-end attenuation and range selection circuitry through a resistor and into one of the inputs of an op-amp. This would be for the high impedance to low impedance conversion and also signal amplification that the meter requires. There's this transistor configuration which looks pretty odd, and I sort of glossed over it in the video and said, well, it's like a couple of back-to-back diodes when they're connected this way. And that's sort of true, basically true, but I didn't go into it as far as I'd planned, and every time I do a video, especially on these test equipment items, I show something like this, and then I always fail to really go over it properly. So I decided this time I would make a separate video and just delve into this a little bit more. Why are those two transistors there, and how is it that they work, and what is it that they really do? Let's get into the what do they really do part first. So you've got a wide range of voltages here. The input attenuator should take care of it in most cases, but inevitably what happens is that the input attenuator knocks the wide range of input voltages down to usually a fraction of a volt, or maybe up to 1 or 2 volts, but it's quite often a fractional voltage. In the case of the IM-5225, this is usually 0.1 volts maximum, and it could be positive or negative in relation to ground. And we need to protect this op-amp from excessive voltages so it doesn't get fried. And you might say, well, why would it get up to a higher voltage if the input attenuator is knocking it down to 0.1 volts maximum? Well, that's because, number one, you don't know if the people using the meter have connected it to an appropriate voltage to start with. And secondly, what if the input attenuator is selected to the wrong position? Maybe you've left the attenuator on the 1 volt range, but you connect it up to 1,000 volts. Well, the attenuator is expecting to see a maximum of 1 volt and plans to knock it down to 0.1 volts, but you've connected it up to 1,000 volts. So now you've essentially just put, the better part of 1,000 volts into here. The attenuator may be attenuating by 10, so maybe we knock it down to 100 volts, but that's still more than the op-amp is intended to withstand. You need to do something to clamp this voltage to a safe level before it goes into the op-amp. And there's other variations. They don't always have op-amps. Sometimes there will be a single FET here. Sometimes the circuit will be the input to a monolithic analog to digital converter. There's different permutations of what might happen out here, but they're high impedance. They don't have a very wide range of input voltage before they could be damaged, and you need to prevent this signal here from getting outside of a safe range. And these two transistors connected in this way is an inexpensive, reliable, and simple low parts count solution to the clamping requirement. With that out of the way, how is it that these two transistors, simple bipolar junction transistors or BJTs, can function as a clamp? Let's take a closer look. This is an NPN transistor. This is another NPN transistor. They're almost always the same type, and they don't even need to have any special characteristics. Pretty much any old BJT transistor will work for this application. And it's often one that's the least expensive. Because it's an NPN, you can see the emitter arrow is pointing in the wrong direction. So let's say we had a positive voltage out here, and we need to clamp it to ground, but right off the bat we're going the wrong direction. This is like saying we're going to go into the cathode or pointy end of a diode. Nothing should happen at all, right? And what if it's a negative voltage where we're trying to clamp in the other direction? If it's a positive voltage, you'd expect some current to go this way towards ground. In a negative voltage situation, current would be going from ground up to here, and once again it's faced with a directional arrow on a semiconductor device pointing in the wrong direction. And what's with connecting the base to the collector anyway? So let's break this down. Let's just take one of the transistors, and again it's a NPN type and the emitter is up here, the arrow is pointing in that direction, and we have the base connected to the collector. Well, we know that essentially the transistor has two diodes inside of it. Not regular diodes, but certainly two PN or NP type semiconductor junctions. Transistors of the BJT type are often explained as if you have the equivalent of two diodes inside pointing in opposite directions. In the case of an NPN, the diodes are oriented like this. If we take the base and connect it to the cathode of this diode, we've essentially shorted it out. So we've turned this entire thing into really just this and gotten rid of this. What happens when you don't have anything connected to the emitter of the transistor and we're ignoring the other half of the transistor and you're trying to apply voltage in the wrong direction? So you're trying to make current go backwards through the junction. Well, we know that semiconductor junctions can break down. And if you do too much of that, you'll damage the device. But what are the actual specifications? We have to look at the data sheet for this. What does this transistor think of us putting current going in this direction through the emitter and reverse biasing it in the first place? If there is going to be any current going in this direction, it has to involve a breakdown of the semiconductor junction's functionality. Here is part of the data sheet for a very common type of BJT in the NPN configuration, namely the 2N2222 transistor. I've just excerpted the part that is pertinent to what I'm talking about here. The specification we're looking for is the voltage breakdown, the emitter to base junction being open. So no connection externally involving the emitter to base. So this is what we're looking for. Emitter base breakdown voltage. In this case, the only thing that's specified is the minimum voltage. It doesn't give a maximum. It's saying that if you did have this situation, the breakdown will be at least 5 volts. And it'll also behave, although it doesn't say it in exactly those words, this also means that you're not destroying the device if you do this, and you're going to get about 5 volts across the junction when this happens. And it could be more than 5 volts. They're just saying that it has to be at least 5 volts. So, redrawing it once again, this transistor in this configuration, in this situation, is actually going to behave pretty much like a Zener diode pointing in the same direction. So its cathode is in the same direction as the arrow on the emitter of the transistor. And like a Zener diode, once we start putting current through in this direction by having a higher voltage here, it's going to go into some form of breakdown. It's going to be a controlled situation, and it's going to have a voltage drop across it, which is predictable. In this case, greater than 5 volts. So you could look at it as a 5 volt Zener diode that might actually be a 5.5 or a 6 volt or, you know, a 7 volt Zener diode. At least it'll be more than 5 volts. There's a big difference though. Whereas a regular Zener diode has a wattage value of a fair amount, the actual wattage value on a BJT that's reverse biased and in breakdown is going to be pretty low. It's not a powered device in that mode. If you allow the current to get higher, it's going to fry it. Whereas in the case of a actual Zener diode, in that same situation, it could handle a lot more. So what about the other transistor that's facing in the other direction? So this will be the lower transistor in that pair of transistors. Again, inside the junctions look like two diodes facing outwards, and we're shorting out the upper one like this. So you can redraw that as just this. It's no longer reverse biased. The current is trying to go through it in this direction because the voltage here is higher than this. So it's forward biased. And just like any Zener diode, if this were a Zener diode, it would behave more or less like a regular diode when it's forward biased. And that's the same as just looking at it as a regular diode here in this model of the transistor. So we essentially have this. So now we combine the two transistors here and we get a Zener diode and a regular diode like this. Except of course it isn't a real diode if we bias it in the other direction. So because we can bias this in the other direction, in other words, when the polarity of the input signal, the excessive input signal, is negative rather than positive, the whole situation flips upside down. And now this is the one that's going to be reverse biased, and this is the one that'll be positively biased. So we might as well just draw these things both as Zener diodes, facing in opposite directions. And we know that this is going to have approximately 5 volts or more across it. And this being a forward bias diode, that's assuming that it's a positive voltage here and a lower voltage here. Typical diode is in the 0.6 to 0.7 volt forward voltage drop, so let's just call it 0.6 volts. Drop across that one. Then we combine those, and we have at least 5.6 volts. That'll be across it, but there will be current going through this way, and the bottom transistor is connected to ground in this situation. So we'll be clamping this to no more than 5.6 volts, or whatever the sum of these ends up being. But certainly a lot better than 1,000 volts. Now let's go back and look at this original configuration. If you had 1,000 volts here, and you had these transistors acting like this, 5.6 volts, okay, 5.6 volts will be dropped across it, and the remaining part of the 1,000 volts will be dropped across this. Well, at least it isn't all dropped across this, right? If you left this resistor out and just put the clamp here, it would probably be fine as long as the input attenuator always kept things no higher than 0.1 volt, according to what I said earlier. But again, we don't know for sure what's really going to happen out there, and we don't know what voltage the input's connected to and its relationship to the selected range and associated attenuation. So it could be a lot of voltage out here. So this is the circuit redrawn. Let's say I have 1,000 volts up here, and I've got the 10K resistor. I have the back-to-back Zehners with a voltage across them of 5.6 volts or more, leaving 994.4 volts across the resistor. If we know we have that voltage and we know we have 10K resistor here, Ohm's law says we have 0.1 amps going this way. Well, that's 100 milliamps. And it's not good for the transistor to be subjected to that amount, but it can handle it for a little while. And hopefully the over voltage situation doesn't persist for very long. Anyway, you've protected this because it can't get higher than 5.6 volts. The vast majority of the voltage is dropped across the resistor. So even with just 0.1 amp going through this, because the voltage is quite high, eventually you're going to overheat this transistor. But the supposition is that you're not hooking this up for a long period of time. This is kind of like, oops, you know, momentary connection to something. And even more so than that, you can't really protect this in this way to sustained errors, like you connect it up to 1,000 volts and just walk away when it's not expecting 1,000 volts. You know, when you don't have the upfront attenuator in place and so on. The 0.1 amp isn't going to be enough to blow the 2 amp fuse on the input. However, the most likely source of high voltage here will be from spikes. Momentary excursions of voltage that you just need to clamp down quickly, and then they're gone before anything really gets damaged. And so this solution takes care of those. Those are a much greater likelihood than just somebody being a bozo and connecting the meter up in some goofy way. Anyway, that's how the transistor behaves here, and that's the purpose of this video. Alright, I have a little test set up here. I've got a 10K resistor, and then it goes out through a milliampere meter here, and then comes into the 2 transistors. They're wired up exactly per the sketch that I already showed. The voltage at the front end of the resistor, in other words the unclamped side, is shown up here, and the voltage at the clamped side, this is the point in the circuit that would go into the input of the op-amp or FET or whatever, and that's displayed here. Right now there's nothing happening in the circuit, and I've just got some extremely low voltages floating around that have nothing to do with the circuit. I'm going to take this up to, see if I can get to a point where there's not too much glare. Alright, so there's 1 volt essentially. 0.99 volts. And they're both showing the same thing. Let's go up to 2 volts. They're both showing the same thing. 1.99, 2.99, 3.99, 4.99, so 5 volts still. 6 volts, So 6.99, so it's 7 volts. Now there starts to be a bigger disparity. The input is essentially 8 volts, and the output is only 7.6 volts. Let's take it back down a volt. So we're putting 7 volts in, and we still have 7 volts. The disparity really happens between 7 and 8 volts. The output doesn't really go up. So now we're up to 9 volts, and we still have 7.6. 10 volts, still have 7.6. Go all the way up to 20 volts, and I still have roughly 7.6, 7.7 volts on the clamped side. So this particular circuit is clamping at 7.6, 7.7 volts. What happens if I reverse the polarity? It's a little different. We still have 20 volts. The other one went up to about 8.1 volts. So that shows us that the pertinent specification on those two transistors, it's not exactly the same. As they say in the spec sheet, it's greater than 5 volts. That's all they're going to tell you. It's for sure greater than 5 volts. So this is not clamping at exactly the same voltage when you have the reversed polarity, but it's still clamping. And I can take the voltage back down, and we're staying at 8.1 even as the input decreases. I would expect to see it stay at 8.1 up until about 10 volts, and then it starts to react a little bit. We're at 9 volts, it's clamping at 8 volts. We're at 8 volts and it's down to 7.9. We're at 7 volts and now it's matching. They're both essentially 7 volts. And meanwhile my milliampere meter is showing 1.2 essentially milliamps in the circuit. Doing a little quick math, if I have a 20 volt input, I have a 10K dropping resistor, I'm clamping at 8 volts, that means that there's 12 volts across the resistor. 12 volts divided by 10K is 1.2 milliamps. That's a sloppy 2, isn't it? 1.2 milliamps. Exactly what it's showing there, although here the polarity is negative because I reversed the power supply. Let's get that squared away. Yeah, 1.2. Notice it's a little bit different here because the clamping is happening at a slightly different voltage, but still pretty close to 1.2 milliamps.